Hello, everyone. So this is Lin Yang. So I'm an assistant professor at UCLA, and thank you so much for the invitation. And it's my great pleasure to speak here. And it's also a pity that I cannot participate this great workshop in person due to visa issues. Nevertheless, I would really like to share you some of our recent results in online learning about multi-bandit settings and reinforcement learning settings. Okay. So this talk is about uniform last-iterate guarantee for bandits and reinforcement learning. So it's based on joint work with my students, Eugenia and Yu, Yunfang Li, and my collaborator, Russell Wang. Okay. All right, so let's get started. So this talk is actually about about these settings, right? What we call multi-bandit settings and reinforcement learning setting. So I'm sure many of you have heard about those things, right? So these are about exploring some unknown environments and try to learn some good policies to interact with these unknown environments. So in particular for this multi-bandit settings, which I put a picture here. So there are a lot of arms, right? So you don't know what are these arms, right? So, but if you pull this arm, okay, so you're gonna receive some reward, okay? So basically, you are able to interact with this environment round by round. Okay, so there's another slightly more different environment called reinforcement learning environment. It's not like a single arm you pull that you get a reward. It's like you plan a policy for a sequence of actions and receive a sequence of rewards, but the sum is the total rewards that you care about. Okay, but in that way, you can still, reduce this reinforcement learning problem to bandit learning problem by treat each policy as an action. Okay, so in any ways, right, we summarize this framework as this way, right? So there is a learning agent who wants to interact with the environment for multiple rounds. Okay, so the optimal action, right, is unknown. Okay, so once an action is pulled, okay, so or and policy is played, right? So the agent receives some feedback, right? So some rewards, right? Some state transition, etc., etc. Okay. So, but of course, the algorithm needs to improve its performance in the long run, right? So, what are this performance measure? So, usually people use this common performance measure, which is called, okay, the regret or pack bounds. Okay. So, basically, you want your performance in the long run comparable to the optimal action. Okay. So, more formally, we can define this regret bound as this way. It's a sum of all the suboptimality gaps. Okay, so what is the suboptimality gap? So here we denote it as delta t. So delta t is the measure, it's the difference of the performance of the action you played compared that to the optimal action, right? So obviously this suboptimality gap is unknown to you, right? So the regret is the sum of these unknown quantities, right? So at every iteration, you sum of all these unknown quantities. Okay, so obviously you cannot directly compute this regret, but you hope to upper bound this regret bound, right? This regret. It's a sum of all this suboptimality gap. Okay, so like here, so if we run the algorithm for big T runs, right, the sum is of the suboptimality gap up to time T, right? So you can also look at the sum of T when T goes to infinity, right? When T goes to infinity. So you really want this thing to be small, but for here we see that, okay, if the algorithm is actually effective, right? So the regret bound is actually sublinear in T. In that way, the total suboptimality divided by the total number of runs, right? That is the average regret is converging to 0. It's actually telling you that the algorithm is better and better and is approaching to the optimal arm, right? In some way, okay? So in this usual bound, we wanted this regret bound to be sublinear in T, right? So there's a slightly different modification for this one of this regret bound. There's another measure. It's called pack bounds, right? So pack bounds actually depend on two parameters. So one is delta, which is the failure probability, and epsilon is the suboptimality. So what it says is that, okay, so if you choose epsilon, so if we define the suboptimal arms as any arms, right, that has a gap greater than epsilon, right? So the performance of that arm is more than epsilon away, from the optimal arm, right? So we see that arm is a suboptimal. So this is bounding the total number of suboptimal plays, right? So it's suppose you run the algorithm for infinitely many times, right? So then the total number of plays is upper bounded by a constant function big F, right? That's a function of delta and epsilon, okay? So this is a different measure, okay? So basically, they're measuring the long-term cumulative performance of this algorithm, right? Unfortunately, there are some drawbacks of these algorithms. For instance, suppose we only want our regret bound to be sublinear in T. For instance, it's square root T, okay? So now suppose we already have this algorithm. So now I can do some tricks to make the algorithm very bad in the sense that I can add another square root T many bad plays or arbitrary plays spreading over the known run. Okay, so remember the total number of bad plays I added is at most square root T. Okay, so that only increases my regret bound by another square root T, right? So overall, the regret bound looks almost the same, okay? Unfortunately, the other algorithm add infinitely many bad plays in the history, right? Still, the performance measure gives tells that, okay, these two algorithms almost you cannot distinguish them, right? So that is obviously not okay, okay? So again, for the pack bound, right? So you say, okay, this sum is infinite, or sum from 0 or from 1 to infinity. Maybe that was the problem. Unfortunately, it's not, because this algorithm requires the fixing. I mean, this bound requires the fixing of the epsilon. So suppose the algorithm has a good delta epsilon bound, but this bound, this measure, right, does not bound the total of suboptimality plays if you change epsilon to be epsilon over 2. You may play infinitely many epsilon over 2 suboptimal arms, right? So in both cases, you can trick this bound, right, by adding some very bad plays in the algorithm, and it still looks good, right? That obviously is not a good thing, right? For instance, in some high-stake applications such as medical care, right? So the good performance, the cumulative performance is not good. We really want to, at any time, right? We want to use all the history so that our performance cannot be worse than some function, right? So we really want our performance to constantly decrease in like the picture on the right hand side. So the number of runs is the axis. So we want our performance or our suboptimality is decreasing according to time. It cannot become arbitrarily bad at the future time, right? At the future time, okay. But if you use the previous bounds, right? So I can check that and make it very bad, okay. For instance, like this way on the left hand side, you can add these red points that are very bad place, but the overall regret or tag bound is the same as before, okay. Yeah, I mean, basically the left and right has the same pack bound, regret bound, whatever, but the left case is very bad, okay? So how do we handle the thing, right? So we should call this kind of this kind of a decrease in terms of suboptimality is the instantaneous performance, right? At any time t, we require our performance to be good. You cannot add any bad things into it, right? So to avoid these bad cases, okay? So on the other hand, we really want our overall performance to be good as compared to the left-hand side, right? We want this cumulative performance to be good, right? So basically, we want a metric, okay, performance metric of these online algorithms to capture both cumulative and instantaneous performance, all right? Okay, so now let's look at the literature whether some other people attempted to achieve so, okay? So we find a paper by Dan et al. At 2017. They studied this bond called uniform pack. So it's a modification of the pack bond to avoid the problem of changing epsilon from epsilon to epsilon over 2. Then the algorithm becomes bad, right? So basically what they are doing is that they require that for arbitrary epsilon, you see the epsilon is inside the probability argument. For all the possible epsilon, the suboptimality place, right? Take a sum of that, is uniformly upper bounded by some function f, which is a function of delta and epsilon, right? When this happens with high probability, we can ignore this probability for now. So the failure probability of not, because it's only an logarithmic dependence. So this kind of bound indeed avoids this bad cases for this pack bond, right? Actually, it can imply a very good regret bond, as we denoted here, saying that, okay, if the f function is something like 1 over epsilon squared, then you can get a square root t regret bond. And on the other hand, you can also bound the pack complexity for achieving epsilon accuracy, okay? But the thing is, right, this bond, of course, it's good in avoiding those pack bond issues, right? So does that give us the instantaneous performance? So unfortunately, it's not the case because the summation of the suboptimal place is from t equals 1 to infinity, okay? So due to the same reason, I can implant some bad place of some algorithm that is claiming to be uniform pack, right? So add infinitely many bad place, as long as my bad place is not too big, then the function, I mean, you convert this function of a function of t, okay? So I can claim that our new algorithm is still uniform pack, okay? So in that way, so after I play this algorithm for a long time, I still have the risk of encountering a very bad move, right? So if you just use this kind of performance for the design of the algorithm, okay? So that is the issue. Okay, so what is our solution to this problem? Okay, so ideally we should have another performance measure, right? So this performance measure cannot be too different from the previous measure, and it should imply the previous measure, right? And it should also have an algorithm to achieve it, right? Ideally, we should have we should have all these existing algorithms. By changing them very slightly, we can measure, let's see, satisfy the new measure, right? So that is the idea, okay? So, but is that possible? Okay, I mean, the good thing is that we found this new measure, which we call uniform Last-Iterate guarantee, okay? So what does it mean? Okay, so for here, it's still characterizing this online learning algorithm, where our algorithm is running for infinite many times, right, from t equals 1 to infinity, okay? But here we require an algorithm at any time t, okay, small t, right? At any time t, the suboptimality gap at that particular t, okay? So if you play this, if you follow the action played by the algorithm, right, so at time t, so that suboptimality gap is upbounded, right, by some function of t uniformly for all possible t, okay, from t to 1 goes to infinity, it doesn't matter, okay? So for example, right, we can choose this function f delta t to be something proportional to square root 1 over t, okay, square root 1 over t. As you can see, when t goes to infinity, this suboptimality goes to 0, right? Okay, so for now, let's forget about this algorithm. So is this possible, right? If it is possible, what is the best possible, right? What is the best possible function, okay? So fortunately, we show that this bond actually implies the previous algorithm, previous bonds, right? So in that way, we can derive an immediate lower bound showing that, okay, the optimal ULI function, uniform Last-Iterate function, is actually 1 over square root t, okay? So basically, if you have an algorithm that achieves something like square root 1 over t, then that's nearly optimal, okay? So now we're gonna seek an algorithm, right? We're gonna seek an algorithm where they can achieve this. And if it achieves this guarantee, it not only achieves cumulative guarantee, but also instantaneous guarantee, right? Okay, it's good. All right, so we're gonna show the algorithm. Actually, we show that in the paper. So for this both multi-bounded setting and reinforcement learning setting, we can have good algorithms that achieves URI guarantee. For the multi-bounded settings, okay, it's actually pretty simple to achieve this. Basically, you grab any elimination type algorithm. Basically, this elimination type algorithm, right? So you're gonna run in batches, and in every batch, it eliminates all the bad arms. As long as you can identify the bad arms, you can eliminate those. Okay. So if you run this algorithm in the optimal way, okay, you can show that this algorithm actually holds this URI guarantee. In fact, with the near optimal upper bound, right? So the near optimality is shown here. It's like 1 over square root t, right? Times square root k. K is the number of arms in the environment. Okay. So you might wonder, right? Maybe this bound is kind of trivial. I mean, this kind of a measure, and so all the possible algorithms in the shelf can work without any modification, right? You may wonder like this. Unfortunately, it's not the case. For instance, if you look at this other UCB algorithm, so upper confidence type algorithm, so we show that it's not an optimally UII. In fact, we show that okay. So if you look at this best possible UCB algorithm called Neo's algorithm. So the upper bound, okay, so there is a lower bound on its URI function, which is bounded by 1 over t to the 1 over 4th, okay? So with this one, it can be much bigger than this one we show here, right? Okay. So of course you may wonder, right? So if the algorithm, if is there any instance dependent bound, right? So of course there is, but the details is shown in the paper. And due to time constraint, I'm not going to talk too much about it. So in summary, this bound is going to imply this uniform pack. So it's going to be strictly stronger than uniform pack. So the algorithm that achieves uniform pack may not satisfy URI, but the algorithm satisfying URI is going to for sure satisfy uniform pack. Okay. So for the cases there is no gap, for instance, in the linear bounded setting where the action space is no longer finite, but it's infinitely many actions. Okay, so each action is represented by a d-dimensional vector. So now if you put on an action, the reward is actually proportional to the inner product, right? So the expectation of the reward is proportional to the inner product of the action with some unknown parameter of d-dimensional. Okay. So in this case, we can still show that elimination type algorithm can achieve URI guarantee in an optimal fashion. Okay, but of course, there are some subtle technical issues to achieve computational efficiency. Unfortunately, we design an algorithm that gives efficient G-optimal design every batch. Okay, so that can be used to get a URI algorithm, and the time complexity is polynomial in terms of time d in every round. Okay. So these are the upper bound and lower bounds of URI guarantee for multi-bounding settings. And then we can also generalize these this kind of algorithms, right? We can also look at the algorithm in the reinforcement learning setting. So we design an algorithm that achieves URI guarantee for reinforcement learning setting as well. So reinforcement learning setting, just a brief introduction of that, right? So it's a generalization of multi-bounded settings. You can treat that there's a multiple multi-bounded instance. Okay, so at every time you put in an arm, you're not only receiving reward, you're gonna transition to a different set of arms. Okay, so that it can be a very easy analog of reinforcement learning problems. Okay, so for here we show that okay, this URI guarantee is upper bounded by t to the 1 over minus 1 over 2, right? Again, the near optimum bounds multiplying some polynomial bounds in the number of states, number of actions, etc., etc. These are some subtleties that we're gonna ignore. Okay, I mean, unfortunately, this algorithm will show that it's even though achieving near optimal URI guarantee, but it's not time efficient. Okay, so due to time constraint, let me give you a brief summary of this work. Okay, so basically the paper is posted in the archive. If you're interested, you can have a look. Okay, so we proposed a new metric, right, to characterize the performance of an online algorithm for reinforcement learning or multi-bounded settings. Can be applied to other settings as well. Okay, so this kind of a performance measure capture both the cumulative and instantaneous performance of the algorithm. Right? In the long run, the algorithm needs to be good, and at any instantaneous time, right, this algorithm needs to be good as well. Okay. So we show that, okay, for finite armed bandits, multi-bandit settings, we have this algorithm, all this phase elimination, the elimination type algorithms achieves this URI guarantee with a near optimal bound, right? So unfortunately, this is not the case for the optimism-based algorithm. For instance, UCB, we show a lower bound that does not achieve the near optimal URI guarantee, right? And in the infinite many arm settings, right, for instance, linear bounded setting, it gives the polynomial time algorithm per run, right? Polynomial per run, timer per run algorithm that achieves a near optimal URI guarantee. Of course, the dimension dependence is not optimal, and that actually is an open problem for even not the general regret bound. It's still a open problem about the URI guarantee. Sorry, about the dependence on D. Okay, so this we also achieve algorithm for reinforcement learning settings. So there's some open problems as well. Okay, so that's everything for this talk, and thank you so much for the time. So unfortunately, I cannot be there to answer your question, but if you have any questions, feel free to send me an email so we can discuss either through Zoom or we can meet at another conference. I'm happy to discuss this in more detail. Thank you.